Welcome to Discovering Mega65 with me, Shalan, a series of videos in which I share highlights of my stream on my journey to discover more about the ins and outs of the Mega65. In this video, I take a look at my build environment and the tools I use to deploy to the Mega65, as well as look at some basic first steps in coding. When I started looking into getting a Mega65, KickAssembler didn't have support for the 45 GSO2, so I was a bit worried about that. So what I did is I went ahead and made two files. They are already in my GitHub, but I will update with the latest versions and share them there. So what do these files do? First of all, you have to include them. If you're doing a Mega65 KickAssembler project, you have to include these in order for it to work correctly. First one is sudo opcodes. So obviously in 6502 you've got opcodes like this, but you've also in 45 GSO2 you've got a Z register. So you need a way to be able to write stuff using the Z register, and that's what these sudo opcodes do. They give you these. They also give you some things like map and end of map and map. It's basically just implementing all the opcodes that aren't in 6502. I am slowly updating this with new things, like I've just put these ones in as well. And so you need to include this to be able to do the opcodes that don't exist already in the 6502 set. The other thing that this does include is macros for certain things as well. So one of the things I've got in here is a basic upstart 65. So one of the things that the Mega 65 and the Commodore 65 does, which is different from the Commodore 64, is the basic address is different. So the basic address is at 2001, not 801, hexadecimal both of those. So I wrote a basic upstart 65, which basically allows you to use it as if it was basic upstart 2, but uses 2001 as the entry address here. So the other thing I've done as well, and this is going to grow, is I've added a few of the kind of common things that you'll be doing. So enabling 40 Hertz mode, for instance. Same with the enabling of the VIC registers as well. So the Mega 65 contains 3 implementations of the VIC chip: VIC2, VIC3, and VIC4. So VIC2 from the C64, VIC3 from the Commodore 65, and VIC4, which is the Mega 65 implementation, and by far the best one of the 3. And to enable these, you have to just what's called knock values onto this register here. So knocking these 2 values in this order to this register D02F will enable the VIC3, and knocking these 2 values into D02F will enable the VIC4. So the map memory function, I will explain why I'm using it at the moment. I think I may be able to get around not using this anymore. However, it's a good macro to have in place. So what this will do, this will map 8 kilobytes of memory from your source to a target which lives within the first 64 kilobytes of memory. The other one I've got as well is something I added in when I was testing some font stuff out: set a character location. So the thing with the VIC4 is you're not limited to the first 64 kilobytes of memory. You can use a character set pretty much anywhere in the first 16 kilobytes, I think 16 megabytes of RAM. So that's what these files do. So this is my make file. So what this does is this is loading, first of all, this is compiling the code. And then what it does is it loads the emulator up. Now, the only problem with this, and this is something I spoke to LGB a little bit about today, is that this will only load files that do not exceed the first 64 kilobytes of memory. That means I can't always use this, and I'm going to figure out a way of doing this through a loader anyway. Then finally what I'm doing is I'm using a tool called M65 Connect. Now that is available through the M65, through the Mega 65 GitHub. And what it allows you to do is through the command line, you can launch PRGs over the JTAG connector through USB. And if I try and load a file, it will do the build, it will launch the emulator. Then as soon as I quit the emulator, the Mega 65 will kick in, and then it will load on the machine. So the first thing I did was just do some simple tests, really. Can I do what everybody else does whenever you start a Commodore 64 program? Kind of make the border flash. So let's just show you, actually not the border in this case, the screen color flash. So let me just show you this. I've deliberately commented out some things in here. So there you go. You can see it loading in the emulator here. And this is the effect that we get. We just get these colors moving up the screen. Now this is happening at 1 megahertz. Now if I load that into here, you'll see the same thing happening on the Mega65. So it does look a bit different. So this is one thing you have to bear in mind when you do these things, is that if you are running this on the emulator, it's not going to look the same, exactly the same. There are some differences. If you want to test cycle correct stuff and cycle accurate stuff, you are going to have to run it on the real machine. So one of the things you'll notice on here, if I just pause it by grabbing the window, as LGB says, it's scanline based. So when it sets a color, it's setting it once for that line. Once it's set, that entire line is drawn in that color. Whereas on the Mega65, which I'm not sure, can I pause it on here? I don't think I can pause it, can I? But on the Mega65, you can see the color changes multiple times in a line. So as I say, this is a very, very simple routine. But one thing I noticed is if I don't disable the interrupts here, this is what happens. Let's do it again. Just keep your eye on it very quickly. You see the border colors, the background colors, they change very briefly, and then an IRQ kicks in and clears them. But as Paul just says, the C65 actually uses an IRQ interrupt for a raster interrupt for the keyboard stuff. So by default, D01A is not set to 0, which means if you do this CLI and you enable interrupts, then basically you are gonna, especially if you turn off ROM, which I'm doing here, then you're going to break things. So the next thing to do is to turn it up to 40 megahertz. Yeah, I need to relabel that because I've called it enable 40 hertz. It should be 40 megahertz. And here again is where we can see the difference between the scanline kind of precision of the emulator versus the real thing. So there you can see it's going through the colors a lot quicker now. Okay, let me try that, because if that works, that would be really good. So I'm basically loading all 3 registers and the accumulator with 0 and then mapping. Okay, in that case, what I might do is I might move that into the macro for enable VIC4 registers and enable VIC3 registers, because then it's just, if you enable them, they're there and then it's done. So what I wanted to be able to do was to use Aseprite. This is a well-known art package. It's used by a lot of retro and pixel art. It's great because it has a lot of palettes built into it. So you can kind of pit, like Atari 2600 palettes and things like that. What I wanted to do is I wanted to create a system where I could take a file that's drawn in this, and basically just by saving it out in a particular format. In this case, I'm actually saving it out as a bitmap. And the other thing I'm doing is I'm making sure that color mode is indexed. So I took an image from Quake 3, converted it into 256 color mode, and put it into this file. And then what I've done is I've created 2 scripts. So the first one will take a bitmap and it will create a GIMP palette, and then it will take that bitmap and it will turn it into characters. What I'm thinking of doing though is turning it into a full editor as well. So you'll be able to drop an image in, chop it up, turn it into tiles and a palette, and then use those tiles to generate a map, which you can then load into memory. And that map can be made up of meta tiles as well if you want it to be. What full color character mode is basically instead of using color RAM to define the color of your character, and instead of using multicolor character mode to define the color of your character, you have 1 byte for every single pixel in your character. So this is our character grid here. So you can see there are 64 pixels in here, and each one it can be any color in this block here. So we define this character as 64 bytes instead of 8, and what we define is which index it is in here. And that's all this is. This tiles Q3 dubbing is basically just the output from that file. And then the palette looks like this. Let me load this in here. Which seems a little bit weird that I've gone for an intermediate file format, but the reason I did this was because actually I started with the palette creation first. I found some palettes online which were in this GIMP format. I use GIMP quite a lot, so I was kind of happy to use this. And it's a very easy to understand format. BGR, it's the other way around, so blue, green, red. So I wrote a file which takes those those palette files and turns them into code. And what this code does is it creates a label for each of the colors, because actually in a GIMP file you can have different names for these, and some of the palettes you will import have things like gray 100, gray 200, gray 300. So I created a system which actually creates these palette labels, so you can actually use you can select colors by selecting things like load accumulator with palette gray 300. You can use those constants then, and then at the very end it just creates some byte arrays. So the way palettes work on the Mega65 is they're loaded into a location in memory. Let me show you the second file. Let me just copy all of this and load this into here. So they're loaded into these locations. So the reds run from D100 to D1FF. Green runs from D200 to D2FF, and blue runs from D300 to D3FF. Those palette arrays here, the red, green, and blue arrays here, I import them here, and then I have a little function which just copies them in. You'll notice on the C65 and the Mega65, the default mode is an 80 column mode, kind of like the C128 80 column mode. So there's actually 80 characters across the screen. So the screen is actually 640 pixels wide, or it's called H640 mode. You can turn that off, and you can switch it back. So by turning off bit 7 of D031, so by turning that bit off here, you basically turn off 80 column mode, and you switch it into 40 column mode, which looks more familiar. But now you can see that each line is actually taking up 2 lines, and there's more tricks about how to stop that. So one of the things that the Mega65 has, which is a really nice feature, is the ability to set the number of characters that make up one line of the screen, then the number of characters that are actually drawn on the screen. If I go back to this one again, and I go back into 80 column mode, right, and I run this, you'll see all 80 columns are displayed, right? But if I change this value here, I can say, don't display all 80, just display 40, and it will just display the first 40 on each line. So you'll see there's a cutoff here. The reason for being able to change the length of a line will become more apparent later. I think it's more useful for horizontal scrolling and raster rewrites and stuff. That's where it's going to be more useful. There's also logical characters per row. So if I let me do that as well, let me change that. So let me turn that back off again. So we'll go back to 80 characters per row, and you can see 80 characters here like this, right? Now, if I say, instead of 80 characters, which is here on a row, let's just say there's only 40 characters on a row. Now the screen is still displaying 80 in a row. So what will happen is now it's drawing this line, and it draws this line, and it's perfectly fine. But on the next line is 40 characters long. It's not 80 characters long. The next line is 40 characters long, because each row, I'm telling here that each row is logically 40 characters long. Likewise, if I double that, so if I put it up to 160, it's going to skip lines, because it's going to display 80 characters and then it's going to skip. So you can see I've compressed what's here. And this is really useful, because what this allows you to do is it allows you to create a line which is thousands and thousands of characters long, but only display 40 of them or 80 of them. And then you can move that screen around. So you can have a map that extends tens of thousands of characters in one direction, and then you can move the screen along that. And you'll see that I'm doing something similar with the scrolling when I get to that. And there we go. So what you're seeing now is not a bitmap, it's a character mode. So what you're seeing is 1,000 characters, different characters, all using the ability to use 256 colors. Full color character mode, as I explained, is 64 bytes per character. Each byte defines a color in the 256 color palette, because you've got 0 to 255. Now, obviously, to do that, 64 bytes is a lot. So one of the things that the full color character mode requires is the use of 16-bit character locations. So what that means is the screen RAM here is actually using 2 bytes. For every single character, there's 2 bytes being used. And so what you will see in here is, so I'm setting 40 column mode, so there's only 40 characters across the screen, so 28 in hexadecimal. But logically, the number of memory locations that each row takes up is actually 80. So even though there's only 40 characters across the screen, the actual memory locations are 80 because each character takes 2 bytes up. So you have to set the logical characters per row to 80. If you don't do that, this happens. And you can see there, you get this weird interlaced effect. So yeah, that was kind of my next step. And this was just to prove that the tools were doing their job. So I wanted to get the screen scrolling. So the normal method for this is you set up an IRQ interrupt, a raster interrupt. You cycle through some scroll values, either horizontal or vertical scroll values from 7 to 0. When you overlap and when you kind of overflow, then you shift the screen up. Basically, you take all the data on the screen, all the color data and all the screen RAM or the character data, and you shift it in the direction that you're trying to scroll things. Now, this is probably one of the most painful things to do on the C64, and it's the reason why you have games that have limited colors when you scroll, because obviously scrolling colors is a pain in the ass because you cannot relocate color RAM on the C64. However, on the Mega 65, that is not the case. So what happens on the Mega 65 is you still have the hardware scroll registers, and you can actually see on here, let me just make this a little bit bigger. One of the hardware scroll registers is actually by default, it's off a little bit on the Mega 65. But the cool thing with the Mega 65 is instead of having to shift all the contents of the screen, what you can do is you can just say the screen is actually at this location. So on the Commodore 64, you can change the screen within 1024 bytes. So you can change the screen from 0400 to 0800 to 0C100 to 1000 to 1400 to 1800. So you can change where the screen is, and we use that for double buffering, and we switch between 2 screens very quickly, and it's useful for doing things. And one of the things it's useful for is speeding up scrolling. However, on the Mega 65, you can move the screen 1 byte in any direction. So you can say the screen is at 0400, but now I want the screen to be 0401. Now I want the screen to be at 0402. So what you can essentially do is you can start drawing the screen from anywhere in memory that you want. And it's an incredible feature because what it means is you no longer have to shift any of the color, any of the screen RAM at all. What you can do is, instead of, say you want to shift the screen up, normally you would grab every one of those 1000 bytes and you would move them up in memory. You'd move them backwards in memory, 40 spaces in memory. On the Mega 65, all you need to do is say, the screen is no longer at the location you're looking at now. It's 40 characters ahead of that. And the whole screen will move up by 40 characters. And so that's what I'm doing in this IRQ. So what this IRQ does is it goes through the scroll values. It subtracts our scroll speed from our scroll, and it applies that to D011 like we would expect. But if we overlap, if we kind of wrap around from 0 to 7, what it does is it changes the screen base. It changes where the screen is actually drawn from. We tell it to load the screen at this screen base location, and in this case it's 50000. So this is actually where our screen is here. I've moved the screen data to this location. But every time we move the screen up by 1 row, all I do is I go in and I add 80 characters to that screen row. I add 80 characters because that is our logical characters per row. That's how many memory addresses are taken up by that. And I can move the entire screen up by 1 without shifting anything in memory. All I'm doing is saying, this is where the new screen starts. Okay, so let me show you what this looks like then. So again, this isn't going to run in the emulator, so I've turned the emulator off. And the reason it's not going to work in emulator is because I'm expanding beyond the first 64 kilobytes of memory. I will try and figure out how to do that, and maybe on the next stream we'll get something that does work in the emulator like that. No help in there due to. Oh no, it's fine. This is fine. Okay, so what you're seeing now is full character mode being scrolled. Now the reason why it looks like it's shifting along as it goes is because I've deliberately shifted each screen to show that it's a different area of memory. So each area of memory has a slightly shifted screen as it goes along. And I don't know if you can see this, but you see that tiny little red dash in the bottom corner? That's the entire raster time it's taking to do this. I'm changing the border color to red while it performs this function, and that is how long it's taking. It can do this basically in the border for a single line. That's how quick it is. It is running this in about the time it takes you to change the border color twice on the C64. It is incredibly fast.